You ready? All right.
Well, welcome to the afternoon session of the REU Day 1 Symposium. We're going to start off with Bryce. So Bryce, whenever you're ready.
All right, my name is Bryce Walbridge. I'm here to represent Calvin University as well as SWERI, and I'm part of the BSA REU program of 2022. My mentors are Matt West, and he's online, and Marcus Hughes, who's over there. So first off, I'd like to start off with a little bit of background before I get into what I've helped to develop this summer. I'm going to start with a coronal mass ejection. CME is an expulsion of diffuse gas of ionized particles called plasma at high temperature. And there's a beautiful picture right next to it displaying what a CME looks like. And basically, why do we care? What's the harm? The harm is that it can hurt satellites, power grids, communication systems. Definitely not good if a CME were to hit us or get anywhere in a near general vicinity. Here enters what is PUNCH. PUNCH is a small NASA Explorer mission that there will be 4 of them, and they will be put in low Earth orbit. PUNCH stands for polarimeter to unify the corona and heliosphere. And the PUNCH mission consists of these constellation of these 4 satellites, which are to the next, to the left, no, right, there we go. Sorry, I'm looking the wrong way. And the top one is 3 of them will be wide field imagers, also known as WIFI. And below, there's one near field imager called NIFI. The overall research goal is to study the solar wind, and PUNCH will be monitoring a lot of space weather. And it's slated to launch around April 2025. All right, here's an artist rendition of how PUNCH is going to work as it takes pictures of the corona. You have your 3 wide field imagers are taking wide field adaptations, and then a near field is taking the inner part of picture of the corona. And it is ranged from 6 to around 160 solar radii. And that, if you're familiar with coronal graphs, it's basically going to produce a gigantic one. So going forward, also the PUNCH cameras sense. Just for a second. The PUNCH camera sense normal visible light and its polarization, and the goal is to allow us for 3D location of solar wind features to be measured. So let's start off with what is polarization to give you more of a background before going into the nitty-gritty. So what is polarization? Well, as you can see in the picture that has all the rays coming out of it, that is unpolarized light, comes out in all directions. And when it gets scattered or reflected, it gets lined up in a neatly fashion, like the one that's right next to the image of with a neatly fashioned electromagnetic field denoted by E and a perpendicular field of magnetic field denoted by B. And the direction of polarization is defined by what is parallel to the electric field of the wave propagating through space, and that is the E field. So since it's vertical, it is vertically polarized light. And the definition of polarization is a characteristic of oscillation of the wave-like nature of light. It has a definite direction that is relative to the direction of propagation of the wave. So an example in your real everyday life that might help you conceptualize this is water. So light reflects off water. It gets vertically polarized, or linearly polarized, I should say. And you have sunglasses that you put on that block in a certain direction the polarization of light. And so whatever polarization that the light comes off, the sunglasses will block it in the opposite direction of the polarization, and it will block that light but let other light in. And you can see structure underneath the water, and instead of seeing clouds reflecting off the surface, you'll just see what's underneath the water. And basically, polarization physics kind of works like that too, except it's not water, it's a hot gas ball. So basically with different polarization angles, we're able to see different structures form, and that's the goal of PUNCH, is to look at the solar wind and the different structures that it has. So in polarization and solar physics, there's our goal is to find 3D location of solar structures, and there's a ratio that I will cover closer later on in the PUNCH resolver that's called PB divided by B, and that is what's going to give us chirality, which relates the strength and direction of the magnetic field in the corona to the observed photoelectromagnetic field as defined in DeForester et al. Paper 2017. Chirality impacts geoeffectiveness, and what that means is how much of a geomagnetic disturbance it will cause here on Earth. So, cool. And this image right to the next to the text is a picture of polarized data taken from SOHO and stereo, and basically being put together at a different angle. You can go around, you'll get different structure, and you can extrapolate from the structures of each different angle a three-dimensional plane. So basically, you can start to make three-dimensional structures of the corona and start to see how they look rendered. So polarization measurements. Stereo captures polarized images at three different polarization angles. These images you see on the screen are from stereo. They're real data, and it's polarized at 0, 120, and 240 degrees. Why is this important? Well, so will punch. Punch is going to take in images and it's also take the polarized data the same way. So punch polarization resolver. Now I'm going to get into, this is what I helped develop this summer. I had the honor of developing with my mentors. And the punch polarization resolver, what it's going to be is an open source Python package, not just for punch, but for community use. And it's going to take in 3 polarized data sets, just like stereo produced. And it's going to convert them into images that show more structure, like a total brightness image and a polarized brightness image. And that will be the next slide. So the 3 polarized data sets are different polarization angles, -60, 0, and 60. And from now on, what I'm going to refer to as the 0 and the 120 and the 240 degree pictures that you saw on the last slide, which were here, they are going to be analogous to the -60, 0, and 60 degrees because that was taken on a 180 scale. These ones were taken on a 360 scale, but they are, I can guarantee, the same. So, and that's going to set up our new system called MZ and P. So it's very nice and convenient because M stands for minus, so that's the -60 degree angle, and then it's going to be 0, which is 0 degrees, and plus, which is +60 degrees, which will be transferred to the increased angle with the 360 inch part of the data sets. So in the pictures to the right also explains this as theta Z, which is the 0, and then theta P, which is the plus, and theta M, which is the minus with 60 degrees. It just kind of helps conceptualize it. So there are resolvers that exist out already, but they are only instrument specific, and they're written in different languages too. So since punch is going to be the punch pipeline and the software that's on punch is going to be written in Python, this resolver will be written in Python. And since it's for community use, it's not going to be just instrument specific. It can work on all polarized data sets, so it'll be helpful for research. So converting systems now. So now we're in the resolver part of it, where it's going to start resolving polarized data for us. So we take our polarized data of 120, 0, and 240. And as I said, I'm going to start defining them as MZ and P now. And I promise they are the same and analogous to -60, 0, and +60. So our 120 is defined as our minus, our 0 is 0, and P plus is 240 degrees. And as a polarization resolver, the module will convert these and spit out 2 images. B, which is going to be the total brightness image, which is a combination of MZ and P, and PB, which is our polarized brightness image. And they both show different structure. Let me move this screen for a second. PB and B to a helpful ratio. The PB image clearly emphasizes different aspects of the CME from the B image, but the ratio highlights the 3D structure. This is defined by the DeForest 2017 paper. So we have our total brightness image from the combination of MZ and P, and polarized brightness also spit out part of the resolver with part of resolver characteristics. And what we're just taking, the resolver also takes the ratio, and that becomes important in defining what seeing what chirality is and the direction of magnetic fields in the corona and especially CMEs. Let's see here. Oh, sorry, this is the arrow key. Can't use the arrow key. All right. So, and continuously to test the robustness of our resolver, we're going to use synthetic data as well. We can use real data, but synthetic data is nice because we can make it punch-like. Because it's not launched yet, so we want to make data that's punch-like that takes in to test it before we send punch up and then the resolver doesn't work. However, so we want to make sure that we test the robustness to make sure it's working properly. So we use synthetic data with a program called Forward. And what Forward is a software that is really good at making a lot of different synthetic data. The two pictures I have on here is from the Gibson 2016 paper. And these are both from Forward, and they're coronal graphs as well. One is polarized white light. And what's nice about it is that it makes these polarized data sets that our resolver takes in, so we can test it. So that's really nice. And why do we use Forward? We wanted to produce punch-like data again, just to test the robustness of the resolver. So noise with synthetic data. So synthetic data is very nice, except for it's very clean. And it's not like real data like stereo. There's always going to be noise, instrument-specific noise, and another noise that are put into the images that are inherently in there. So we need to add noise to make it more realistic and punch-like. So these images you see is before and an after noise image. We have a program that I would like to give credits to Chris Lauder that developed that generates a variety of noise that adds it to our MZP images. And as the resolver converts from MZP to total brightness and PB, the noise is transferred over to the next data sets. So the noise is added. And so we wanted to test it to make sure that we see noise, and before and after images, you can see one is completely nice and it transitions really smoothly. So that's the synthetic data. And then we have synthetic data with noise that you can see is more hazy. That means that there's something added, and that's the noise. So we want to generate forward synthetic data and add noise, which we did, and evaluate how the noise affects the specific MZP triplets at the beginning. So continuing with noise within synthetic data, the next slides will show polarized brightness and total brightness and the ratio PB over B, clean and with noise. Each clean and noisy pair has the same color scale. Just to give a disclaimer. So here's one picture right here. I took the log to show you the differences more specifically. There's the clean image of synthetic data. And then this is for total brightness using our MZP triplets combined. And then we have a noisy data off to the right, and there's definitely a difference. You can tell that that noise has been added. And so we seem to see that it's working. Now here's a log scale of the polarized brightness. We have our clean image, and then we have our noisy image. And as you can see, there's a lot of changes, and it looks more hazy. There's more noise added, and you see that all these NAND values included as well. So the ratio between PB and B, that's something that we also want to know for definitions on structure and chirality, and it's also used in 3D location, which is another part of what we want to do in the future. That's defined in the 2017 DeForest et al. Paper. So when we create this ratio of polarized brightness divided by brightness, we get a before image with the synthetic data. It looks really nice. You can see these loops of the corona that are definitely cool. But it's synthetic data, it's too clean. So we add the noise. After the noise, you can start to see that it is more hazy. There's different transition. You can still see the loops, and the structure is the same, and they're on the same scale, but it added noise, so it changes the color a little bit. So going into the evaluation of the noise effects, here we have a total brightness difference and a polarized brightness difference. And I wanted to analytically look at the noise and make sure that things were added correctly. Is it well behaved and it's not blowing up? So with the total brightness difference, we just took the total brightness with no noise and the total brightness with noise, and we subtracted them and made a histogram, and we see a Gaussian. It's nice and well behaved. And we did the same thing with polarized brightness, and just subtracted the no noise minus the noise, and that we have a wideband that's nice and well behaved. Now, I know somebody's going to ask a question on this, so I'm going to explain it here. You'll see that the brightness and the brightness with no noise and the minus with brightness with noise is centered around a negative number, and that is because when you add a bunch of noise in the MCP triplets to make the total brightness, you're going to get a higher value within the noise, and because you can see by the equation down below, you'll get a negative number because it'll be a higher brightness value. So, and then, but also what's really cool about this slide is that there's a definite width to these Gaussian graphs, and the definite width, it can correspond to uncertainty in our data. Now in the DeForest et al. Paper from 2017, it also has equations that predict the uncertainty when you add noise to data. And so what's really nice is that it's well behaved. So we can measure the width, and in future work we can test it with the equations that he has that in the DeForest et al. Paper that and confirm that the results are close in the uncertainty measurements to continue to test it. So, in conclusion, we developed a package that converts polarized data triplets into MZ and P and into polarized brightness and total brightness pairs and vice versa. We validated the polarization resolver with real stereo chronograph data and synthetic data generated with a high altitude observatory forward code. We also conducted initial tests of the resolver to see how it handles noisy data, specifically with added punch like Poisson noise. And right here, and for future work. So our goal is that our goal is we want to replicate the results in the DeForest 2017 paper. The image you see above is a picture of a corona of the corona of the sun, and we have the brightness picture and we have the polarized brightness picture, and you can see they're different, as well as the polarized brightness divided by total brightness ratio, which is in the same structure that we were working with our research. So our goal is we want to replicate that to make sure that a resolver is robust, it's doing everything that we expect, and it's working well to produce data that we can use for observations. The polarization resolver will be used on punch data post-launch. So that's the goal for the far future, is after it launches, we can use the software to resolve the images that punch is taking of the sun. And we will use the polarization to reproduce the results, as I said, from the DeForest 2017 paper, and use the elongation angle to determine the 3D location of solar wind structures. And in 2017, he defines an equation that helps us solve for elongation angle, and that uses the polarized brightness divided by brightness ratio. So it's good that we have that too. And we will also explore the impact of noise on 3D location. So as we add noise, how does that change the 3D location of structures? Does it vary? And how much does it vary? And how much does it impact? That's what we'd like to figure out. So this is my acknowledgements and reference slides. I'd like to thank the Boulder Solar Alliance, Southwest Research Institute, the National Science Foundation REU Award, and the Punch NASA Small Explorer Mission contract number, and the forward package, which is defined by 3 up above by that paper. And this right here is a picture of a corona, a CME that was produced by using the polarization resolver step-by-step images, which I was pretty proud of. I love the image. It's something I got to help with create. And that means, and with these polarized data, you can actually show a different structure in movie, and it's really pretty. You can see as it propagates through space. I love it, and it's something I'm very proud of. So, and thank you for listening. And if you have any interest in more about Punch, I'll have a poster Friday, as well as I have literature for you if you would like to read it. So thank you. And any questions?
All right.
So you had NANs in your synthetic data, like right there.
Yes.
Do you anticipate you will have NANs in the actual data, or where did that really come from?
That's a good question. So the white stuff that you see here that looks like Christmas, but it's not, is not a number of values. And that is because we took the log of our polarized brightness image. And if there are negative values in our polarized brightness image, you can't take the log of a negative number. It's undefined. So we define those to be nans. And that's why they're characterized as white. I would personally wish they were black and not white to kind of, deter it from the image, but that's what we defined it as. So I hope that answers your question.
Any more questions? All right. Thank you so much, Bryce. Next. Oh, is there a question on Zoom? Okay, cool. Thank you, Bryce.
Of course.
All righty. Let's see. Wendy. Let's see. Where's the folder? Oh. promise. Sorry, I used.
Just do presenter view.
Okay, wait, and before you go, I'm gonna move this so it's not.
Where do you want this?
I'm not sure.
It's more comfortable to read it.
Yeah.
Does this work?
Yeah.
It
So
does.
just either leave it here or pull it over.
Okay.
Be good. If this is bothering you, press that little arrow, it'll make it go to the bottom.
Oh, here. Let's see. Let's get the faces.
Oh, gosh. My
Bring
faces.
these. Yeah. bring it over.
We can bring them over.
Press
there.
press this button.
There we go. All right. Am I too loud or is this good? All right. So hello, everyone. My name is Michaela Deaver. I'm working with my mentor, Alexandros Strapassis, sorry, as well as Peter Tatum and Ramesh Kutsi on the evaluation of multi-point estimates of magnetic field gradients in near Earth space using MMS data. Bit of a wordy one, but it's a very fun project, I promise. So what exactly is MMS? Well, it is the magnetospheric multiscale mission, basically a NASA mission that uses 4 spacecraft. And in its history, it uses 4 spacecraft to investigate the magnetic reconnection in the boundary regions of the Earth's magnetosphere. In its history, it's had 2 major formations, as you can see here to the right. It's had the original formation, that was its original formation when it launched in 2015, as well as its campaign formation, which was the collinear formation that happened for about 2 weeks in 2019. This mission provided unique measurements of the solar wind and turbulent fluctuations along a singular direction. As for why we would want this information, there's a few reasons. But the main one that we're going to be focusing on has to do with multi-spacecraft missions in general. These missions allow for the calculations of gradients of the magnetic field, which can be used to calculate electric current. With multi-spacecraft, we can use 2-point measurements to calculate delta B, and then use it to calculate an estimate of derivatives, which is this equation on the top right here. From these, we can use these estimates to assume that the magnetic field varies linearly between the 2 points, which basically, with our collinear formation, allows us to test the assumption that the magnetic field varies linearly between each pair of spacecraft, and then thus the gradients. So to put it in one sentence, you can assume that our delta B here in the top right is just the difference in 2 magnetic fields, and it's linear, which means that delta B over delta X is similar to that partial derivative of B along X. A lot of math, I know. This is important though, due to the fact that in space, when we use these multi-spacecraft missions, we need to know how far we can let spacecraft drift from one another before we correct their formations, unless we want large errors. So how we're going to use this for my project or our project, we want that collinear formation to allow for the assumption of linearity between a pair of spacecraft. Basically, this allows for the use of linear approximation for interpolation and extrapolation. In other words, it's kind of like a first order Taylor series. As for how we would use this for the MMS, we just use 2 spacecraft for the estimate, and then the other 2 spacecraft for the testing of their accuracy. With this calculation, we can get the estimates of the interpolation and extrapolation along the line formed by the first 2 spacecraft. As to how we pick our spacecrafts and our pairs, we kind of have to look at the order of our spacecraft, as you can see here. We are working with 3D coordinate systems, so we kind of had to look at them in planes. So on the top here, we have our XY, our middle, we have our XZ, and then our bottom, we have our YZ. I know this is a little hard to visualize for me, so I made this really helpful plane. So once again, we have on the top our XY, and then our XZ, and then our YZ here. With these graphs, you can see that the spacecraft are pretty closely aligned along the same axis, with separations that can vary about from 30 kilometers to 200 kilometers, with that 30 kilometers being those two inner spacecraft and the 200 kilometers being those far outer ones. Depending on which pair you choose, we can use these measurements between spacecraft to estimate the quality of our linear assumption and then our approximation of the magnetic field. For our purposes in our research, we're using these two cases of the line between MMS 2 and 3 on the left here, and then MMS 2 and 4 on the right. On both of these graphs here, you can see that the x-axis is the distance between each spacecraft in kilometers, and then the y-axis is that magnetic field in nanotesla, specifically here for the the x component. Both graphs also have these green dots here that are all in the same place, though they may not seem like it. They're also in the same timestamp, so that the first time zone or timestamp, and they're the actual measured values of the spacecraft's magnetic field. The blue line we see is simply like the linear line drawn between each pair. So on the left, we have 2 and 3, and on the right, we have 2 and 4. The red dots are interpolated or extrapolated guesses. In our case, we're looking at these 3 cases. On the left here, you're seeing the interpolation of MMS 4 between 2 and 3, so that 200 kilometer distance. And then you can also see that there is about a distance of 0.04 nanotesla between our guess and our interpolated value. But on the left or on the right here, we have our interpolation of MMS 1 with that difference of about 0.02 nanotesla. So we are already seeing a difference between the 2 interpolations, but as we'll see in later slide, that's not always the case. Also on the right, we have the extrapolated value of MMS 3 that we're going to be looking at, which is about 100 kilometers away from our other spacecraft. And then you can see that big difference of about 0.08 nanotesla. This will let us know how far out we can use our linearity assumption in terms of the other 2 interpolation cases. As for why we are, as for why we are wanting to look at these 3 cases specifically, we basically are looking for these reasons. We want to compare the interpolations between MMS 2 and 3, which were that distance of 200 kilometers, and the interpolation between 2 and 4, which was that distance of 80 kilometers. And then we also want to compare those 2 interpolations against the extrapolation of MMS 3 from that 2 and 4 line, which was that 100 kilometers away. This will let us kind of figure out if there is any significant difference in extrapolating versus interpolating with that linear assumption, while the first case will let us know if there's any difference between interpolation at small versus large distances. We are also examining the difference between the interpolated values and the measured values of the magnetic field, as well as that difference divided by the magnetic field as a percent. You can kind of see these calculations below on the bottom of this slide, with the difference giving us our estimate of how well we're looking, and then our percent telling us how good that difference is relative to the magnetic field. So what exactly is our data? Well, we're looking at about a time series of MMS 1 from that MMS 2 and 4 over time. We're only using about 25 minutes out of the 5 hours of data because my computer cannot handle more than that. It's also due to just processing speeds in general, and then we're just trying to get as much of a resolution of that magnetic field as possible. As for the visible representation here, we have our difference in interpolated versus our actual on the y-axis, and then our time in seconds on the x-axis. This just gives us a glimpse into what our data should be looking like with that minimum difference between the x, y, and z components. We can see in like the green, the blue, and the orange. And then there's also that range, that basically has a median of a 0 with no big deviations. So as we look more closely at our results with histograms, yay, we can start off here with the MMS4 interpolation based on that MMS2 and 3. And this was the about 200 kilometers away from each other graphs. And we can see on the left here is our percent error versus the number of events. And then on the right here, we have our difference of expected versus actual in nanotesla versus number of events. As for standard deviation of these two graphs, we have on the right, the difference was about 0.027 nanotesla to 0.03 nanotesla, with the percent error having a standard deviation about 1% with an outlier of 230% for the Y component. As for why this happened, basically the Y components, has a very small values for some of the data. So when you take a small value, have the difference, and then divide it by an equally small value, you get a very large percent error. And so for our next graphs, we have our difference in our MMS1 interpolation based on MMS2 and 4. And then for this, we have a standard deviation for the difference of 0.027 to 0.03 nanotesla, and then a percent error of about 1.1%, which is very much similar to our last interpolation, which kind of gives us a glimpse into what our conclusions are going to be. Once again, all of the components all have similar values and ranges with a median around 0. And then our percent error here has those wider ranges for the different components. And then we can actually see on the graph, there's a light green section, which is just the X coordinate, and we have a slightly darker section, which is that Y coordinate system coming in, and then that dark section, which is just the Z coordinate. On our last result, we were focusing on the extrapolation of MMS3 based on 2 and 4. From this, our standard deviation is about 0.062 to 0.071 nanotesla, and our percent error standard deviation is about 2.58%, with that Y outlier about 96. Strangely enough, we have about a double our interpolation results here. But we can still see that those wider ranges on the percent graph, and then basically the same difference graph. But what is strange though is that our x-axis is also double. So kind of have our double values here. So in summary, Y coordinate component has a higher standard deviation due to those small numbers. And then other than that though, we did see that percent error has slightly different distributions with a similar median around 0. And then that difference of values, histograms, all have a median around 0 as well. And then our difference in expected versus actual values is all similar in all X, Y, and Z components. So going back to our main takeaways here, we were comparing 3 cases, examining the difference of interpolation and extrapolation at 100 kilometers and then the 280 kilometers. From our limited study, this is a limited study, we're basically seeing the following conclusions. When interpolating at distances of 280 kilometers, there's not a significant increase in error or values. Extrapolated data at 100 kilometers compared to interpolated values basically doubles with a deviation of 0.03 nanotesla based on what component is examined. And there's also not a significant difference between the coordinate components in any of the cases. So we can assume linearity of the magnetic field with a distance of 200 kilometers to approximately between 0.027 to that 0.071 nanotesla, which is basically 1% of the background magnetic field. In other words, linearity doesn't appear to be sensitive at distances of 80 to 100 kilometers, and the linear assumption when used with like those 2-point measurements appears to hold within that 0.03 nanoteslas. And then there's no strong sensitivity of distance between spacecraft, at least at these distances. And I just want to say again, this is important due to the fact that if we have those 2-point measurements for gradient estimates, we need to know how far spacecraft can be from each other without getting large errors. And that's it. I just like to thank my mentors and then all of the REU coordinators and helping set up everything. And anyone have any questions?
Thank you so much, Michaela. Yeah, any questions?
You mentioned that you used only a small fraction of the data because of computation resources limits. Do you have plans to extend and figure out a way to use all of the data? Would there be a benefit?
I personally don't know how to do that. I'm not much of a coder. If anyone does have any ways to do that, please let me know. My computer overheats with just like 200,000 out of the 2 million points that we're using. So if you have any ideas, please let me know. Anyone else?
Okay, just to make sure I'm understanding correctly, the goal of your project was to ensure that these small misalignments are not causing any errors, correct?
That could be one way to take it, or
Okay.
another way is basically saying how far can we put our spacecraft
Okay.
from one another before we get those large errors.
So the
around.
goal isn't to line all 4 of these. That doesn't need to happen.
No, like in,
Okay,
in
I
space,
see.
it's not really a straight line. It's kind of a
Right.
ish line. So we just need to know how far can those go before we get
Okay.
really bad values.
Perfect. Thank you.
Any other questions? All right. Thank you so much, Michaela, again.
Great.
We'll be transitioning to another short break.
We are, just so that you know, they are not ready for us quite yet. We're ending just a little bit early. The person at the front desk will be setting up refreshments outside of this room in about 5 minutes. So there will be coffee, hot water, some cookies. So maybe take a restroom break, walk around a little bit, and then come back here and you can get some refreshments. And then we'll come back here. I think the schedule says at 2:15 for Garrett's talk.
What do I do with the microphone?
I gotcha.
I also completely forgot to take off my mask.
That's okay. How do you feel?
I felt like there was a lot of numbers to throw at people.
You want me to redo the title?
Yeah, if you want to just start over, you're all.
Okay.
Sorry about that.
Well, hello again, everyone. My name is Garrett Zills, and like I said, my mentor is Serena Kriskuli, and today I'll be talking to you about the variability of solar H-alpha, calcium-2 infrared, and the calcium-2K emission line as measured by the integrated sunlight spectrometer at Solus. Spacebar does not like that either. Okay, so brief outline of what we'll talk about today, go through some background behind what our project entails, have some research motivation, talk about the data sets from Solus and how they obtain them, go through the computational methods, so the analysis we're going to be doing, go through a little bit of our results, and make some concluding remarks. So first things first, when we're dealing with the introduction, one of the tools that we're actually making using very heavily in our project is spectroscopy. So we're using spectral data, of course, from Solus. And what spectroscopy does for us is it actually shows us what exists within the stellar environment. So we can have absorption and emission spectra. So that tells us what's going on in the sun without us ever having to take any measurements there. And so it's very useful when dealing with stars in general. And it's very helpful in the case of solar physics because the sun is pretty hot. But we know from atomic physics where these lines are. And specifically the lines we want to look at are in the chromosphere. And so this image here is showing just briefly what some of these lines kind of look like. And so this plot is actually showing Vega and the sun. Vega is in blue and the red is the sun, just because it's a little bit easier to see. And it's showing the flux per unit wavelength. And what we can see is actually these very clear absorption lines. So we have the wings, which are coming down, and then anywhere there's this deep dark absorption, in the case of these lines we're looking at, this is the Balmer absorption lines. We're looking at hydrogen. But basically what you can see is that these deep absorption lines occur because hydrogen is changing in energy level. And so for our project specifically, we're going to be looking at this deep absorption line here. But in the case of our sun, not just Vega, of course, is not what we're looking at. But in the case of the sun, this absorption line could be zoomed in. It could be very apparent as it is in this graph. So specifically, like I said, we want to make sure we're only looking at chromospheric lines because our project deals with the chromosphere. And so in the case of how we can make sure this is the case, so from this plot over here on the left, we can see that if you plot out the relative height and the temperature, you can see that the chromosphere is defined as the region after the temperature minimum in the photosphere. And it's before that transition region into the corona. So this brief little region right in here is what we define as the chromosphere. And so we know specifically what kind of lines can form there. And some of the wavelengths, or some of the lines that we specifically want to look at for our project, most specifically the calcium-2 H and K lines, these are very good diagnostics for looking at the chromosphere because they follow the same behavior as the magnetic activity. So throughout the solar cycle, these calcium-2 H and K lines are very good at diagnosing how the behavior and how the magnetic activity of the sun is behaving. And then some other lines that we're going to be focusing on just to compare back with these are the H-alpha and the calcium-2 infrared lines, which are longer wavelength diagnostics when compared with the calcium-2 H and K lines. And so like I said, what we're trying to understand is how the chromosphere affects these lines because chromospheric heating, which is a byproduct of magnetic activity, is actually going to change some properties of these lines, such as the width and the core intensity. And so just a little bit more motivation about why this would be important. Like I said, this calcium-2 H and K lines, they're very, very useful when dealing with the sun because they follow the magnetic activity like perfectly. However, in the newer missions like Gaia and James Webb, these perform only longer wavelength spectroscopy. And the calcium-2 H and K lines, as it says, are 393.4 nanometers and 396.9 nanometers respectively. And Gaia and James Webb, they perform longer wavelength spectroscopy like from 600 nanometers and up. And so there's no information about this calcium-2 H and K lines when looking at other stars. So we can't really understand how the chromosphere is behaving in these other stellar environments as well as we can with the sun. And so in order to mitigate that, a lot of research has been done involving H-alpha. And H-alpha 656.28 nanometers actually correlates very well with the calcium-2 H and K lines over the course of the solar cycle. But it's got some discrepancies in where it originates from. So there's some reason to do further research. So the project that we were specifically trying to understand is how does this calcium-2 infrared line of 854.2 nanometer, how does that behave with relation to H-alpha first, and then tying it back together with this calcium-2 H and K line from the beginning. Okay, so where do we get our data from? So the integrated sunlight spectrometer, as it said, is operated by Solus, which is operated through the NSO.
It's a ground-based spectrometer and it treats the entire sun as a star. So it's disk integrated data. So you account for everything going on in the sun and you get nothing like about the regions, but it is very good at doing the spectroscopy analysis that we're trying to do for H alpha and the calcium 2 infrared lines, because we don't need to know where it's happening. We just need to know that it's present. And this instrument was actually working from 2007 to 2017 before the instrument shut down to be moved. And the other data set that we're going to be using is the calcium 2K emission line that I talked about. And this one's not quite as straightforward to use. So we're using the index created by Bertello et al. In 2017. And basically what he's done is he's combined the data from the integrated sunlight spectrometer with the SAC peak data and this codecanol data. And he uses only the time series data for this calcium 2K emissions from 1976 to 2017. So we have a much larger range of the data for this calcium 2K emission line as compared with their H alpha and our calcium 2 infrared data set. So we have to trim that down, of course. But most importantly, what we're trying to understand with these diagnostics is how they relate to one another. So like I said, this calcium 2K emission line follows the sun's magnetic activity very well, but it's not readily available on these current missions. And we know that H alpha correlates pretty well with this calcium 2K line and is readily available for stellar observations and newer missions. However, there's some drawbacks. As I said, it's kind of controversial of where H alpha can originate from. So this calcium 2 infrared line would get rid of that controversy about like, this is a purely chromospheric line, and this would be a good step in understanding how chromospheres in general behave. So basically the result we're trying to see is which longer wavelength diagnostic between calcium 2 infrared and H alpha actually correlates best with this calcium 2K emission line and therefore the magnetic activity of the sun. And again, just to kind of reiterate what we're saying is the first step that we have to do in our analysis is take the H alpha data and compare it with this calcium infrared data set. And of course, to do this, we need a common observation timeline, just make sure that they have data on the same days. And we have to take both the core width and the core intensity. And so then we're going to see how the core intensity and the core width of each one of the diagnostics correlate with one another. And if they're positively correlated, we want to see like, how does this correlation change over time? Because just because the entire data set is correlated pretty well doesn't mean that that correlation is constant throughout the activity cycle of the sun. So we have to be able to have a pretty good diagnostic that's pretty stable. And so then once we've established that these two longer wavelength diagnostics do in fact correlate with one another, the next step that we want to be able to do is reproduce the analysis for H alpha with this calcium 2K emission data, just to show that those two still are correlated. And then see how this new index, this calcium 2 infrared data set, how does that relate back with the calcium 2K emission line? And from this, the ultimate thing that we can get is a better model of the chromosphere in general. And so we can understand how other stellar environments behave. All right, so getting back to that observation timeline, there's a little bit more to it than just making everything from 2007 to 2017. Because as you can see right here in the middle of 2014, they kind of had a mishap. So they had to move the instrument, and they moved it up into a different layer of the atmosphere. Basically, they moved up a mountain. So now there's different amounts of atmosphere that the lines have to go through. And so that's kind of a mess. So what we did is we just kind of limited the analysis from 2007 to the middle of 2014. So now that we have all of our data in the right format and we have this common observation timeline, the next thing that we wanted to be able to do is actually obtain the data that we want to look at, which is the core intensity of our specified diagnostics, the calcium 2 infrared line and H alpha. And so what's shown here is just a very zoomed in portion of a spectral graph. And what you see is the wavelength as a function of the scaled intensity. But you can see that there's these wings that have these little telluric lines from going through the atmosphere, which is not what we're concerned with at all. All we care about in these graphs is getting this core intensity, so the intensity at the very bottom of the peak. So in order to do that, what we're doing is we're fitting the minima with a parabola, and we're saying this is a pretty good estimate to what the core intensity should be. And so to do this, just in our analysis, we took 15 points on the left and 15 points on the right, and we interpolate what the minimum value is. And then from this, we're going to do that process where we see the correlation between the two intensities of the longer wavelength ones, and then come back and see how well that correlation changes over time, as well as checking the correlation between these intensities with that calcium 2K emission line. And so again, just to show all of the data in one place, we have the core intensity of H alpha as a function of time, the core intensity of calcium infrared as a function of time, and this calcium 2K emission index as a function of time. And all of the analysis, again, just to be clear, is going to be from 2007 to 2014. So if we do the first step where we plot out the two longer wavelength diagnostics with one another, we can see that when we plot it out, we have a pretty positive correlation coefficient of 0.62, which indicates that our longer wavelength diagnostics do indeed correlate with one another, which is a good thing, because then we can proceed with the analysis and say that yes, calcium infrared might be useful. But as I said, we also want to see how the correlation changes over time. And so in order to do that, we're actually going to plot over here on the right, the correlation coefficient over a 4-year temporal window over time. So basically what we've done is to get this first data point here in this scatter plot is we take the data from 2007 in the first point up to 2011, so a 4-year window, and we take the correlation coefficient, which is just going to be that first point. And then we're going to move over a day at a time. So we're just taking a running correlation. And we can see that as we go from a solar like quiet time, so a minimum, up to the solar maximum in about 2014, we actually see that the correlation coefficient increases quite a lot. So the case for H alpha and this calcium infrared index, we actually get a variation in the correlation coefficient of about 96%, which just means you don't really know what it's going to do over the entire solar or entire magnetic activity cycle, because it could be anywhere in here when you look at it. So you don't really know like a good proxy for where that is. But when you come in and you do the next step in the analysis and you look at the core intensity of H alpha with this calcium 2K emission line, you can see that these two, again, are positively correlated, as has been previously found that the H alpha is pretty positively correlated and it has a similar behavior to this calcium 2K emission line. And if we take the correlation coefficient over time again, we can see that it ranges from about 0.3 up to 0.6. So again, it has about a 93% variation or relative variation in the correlation coefficient, which kind of makes it a little iffy to use it as a proxy, because again, if you have this starting at 0.3, you can maybe infer that it's going to go to 0.6, but if you just get this at some random time point, you don't really know where it's going to be at the end of the cycle. So you need something that's not going to vary a whole lot to be a very useful diagnostic. So this one, while it does have a pretty strong positive correlation overall, is a bit iffy to use as a proxy when dealing with calcium 2. So the next step, like we said, we want to look at how this calcium 2 infrared line relates back to the calcium 2K emission line. And we see that the correlation is a little bit smaller for the intensity here. It's actually 0.59 for the entire data set. And if we plot out the correlation coefficient over time, it only goes from 0.4 up to around 0.58. It does have a much smaller variation, which would make it a good proxy, like I said. However, it's not the best because the correlation coefficient is so small in this case. It doesn't ever get above 0.6, which is kind of problematic when you're trying to deal with these as being proxies. So since we've done the intensity analysis and we've come up with some kind of conclusions there, the next thing we want to be able to look at is how does the width behave? Because the width has also got some interesting qualities to it. And so in order to plot out the width, we first need a cool way to calculate it. And so when we're looking at these spectrographs, again, basically what we want to be able to do is fit this and get the width of these cores. And so this is kind of an area of interest because there's a lot of different ways to find the core width. But for our case, what we've done is we basically fit this core that as seen here. And when we fit it in these little spectral ranges as shown for calcium 8542, you can see we go from 854.13 to 854.28. We fit that with a big Gaussian basically and take the full width of half maximum. And we're estimating that as being the width of the core in general. This has some drawbacks to it, but this is the way that we've estimated the width, and that is how we perform the analysis. And so if you look at how the data sets actually look when you take the width, you can see this little behavior that was present with the intensities as well. You can see that starting in 2007, we have smaller widths, and as we increase towards that maximum in 2015, there's a clear increase in the data for both of the diagnostics. And so now we want to be able to see how the two longer wavelengths diagnostics correlate with one another again, and we see that there's a pretty strong positive correlation of 0.67, and that the correlation does change with the magnetic activity cycle again, so it goes from 0.4 to around 0.65, which just indicates that yes, this is also like the width of calcium is also something we can use to perform an analysis and see how we relate to it. And so once we do the analysis with H alpha, which is already pretty well established, we see that the width of H alpha correlates with this calcium 2K emission really, really well. So we have a correlation coefficient of 0.85, which indicates that these two are following almost a very identical path. And then we see that the correlation coefficient over time stays above 0.6 throughout the entire quiet and active parts of the solar cycle. And we see that the variation is only 25%, meaning that this is a great proxy to use when you want to be able to look at chromospheres and other stellar environments. And so finally, if we look at how this calcium-2 infrared line did, we see that H alpha is the better diagnostic because the core width of calcium-2 infrared with this calcium-2K emission line only has a correlation of 0.51, which is still a positive correlation, and there's still very little variation to it, but it's not nearly as high as what we saw with H alpha. And so just to wrap everything up and show what exactly we conclude, we see that if we plot out the core intensity and the core width, and we take the correlations between the two longer wavelength diagnostics, they are positively correlated, so we can perform further analysis. And if we reproduce the analysis performed with H alpha, we see that H alpha is clearly the better diagnostic because the calcium-2 infrared line has such smaller correlations. Also, the variation between H alpha is much smaller than it was, well, not much smaller, but it is smaller than it was for the calcium-2 infrared line, meaning that overall, the width of H alpha best traces the chromospheric activity for future missions. And this does agree with this analysis of spatially resolved observations and models from Kudzi et al. In 2009. And I'd like to take this time to thank my mentor, Serena Kriskuli, who I think is on Zoom, and the NSF and BSA. Thank you.
Thank you so much, Garrett. Any questions?
In your timeline plots of correlation, I saw there were jumps. Do you know what's the cause of those?
Let's get back.
Yeah, for the example, there's one right here, like around 2009 in December. See how it goes up and then jumps down and then.
So that jump up from being up here and like you're asking why it goes back down. So I think, I'm not super sure, but like in these plots here, this was my reasoning about it. So from like 2007 to 2011 would be that little 4-year window there, and there's a lot of points. So my thing that I could be a little off in this, but since it's going day by day in that time period window, I think there's days where it's not getting as much data over that 4-year window as others. So it kind of makes that jump more apparent because there could be a few days where it's not got enough data to like have a very constant correlation. So they're not just right on top of one another, which is why that gap could be present in the plot.
Okay, thanks.
Yeah.
Other questions?
So I had sort of a related question about those plots. You, in addition to those jumps, you also see that like steep ramp. Yeah, right there. Any thoughts on that? That's kind of interesting.
I have not thought about that one, but I have. So this would be from 2011 to 2015. So it would just be a very increasing. Yeah, that's a good point. That would be like a higher activity area for sure, but I'm not super sure of an answer.
Yeah, it might be something worth looking into.
I might comment on that. It seems to me that when you are in the quieter years, there is really no correlation. Yeah, these indices really don't tell you too much in terms of where the magnetic fields are and so on. Don't forget that the calcium K index that you're using is mostly photospheric, while the other things that you're doing here, both the core and the width that you defined, are mostly chromospheric.
Right.
So when you have very quiet areas, the two things really don't care one another in terms of intensities and so on. When you have active regions or stronger activity in general, the two things start, for reasons related to radiative transfer, essentially. So they start going.
Just to piggyback off that, I have a question then. So basically, my interpretation was that the calcium K line forms in a very similar region to H alpha, and that the infrared line was a little bit more chromospheric than the two of those. No? Okay, I'm sorry then.
Now, of these three, again, maybe Serena can comment if she is around, but the core of the lines, of all three lines, is chromospheric. If everything were equal, calcium 2K would be formed higher, H alpha would be formed a little lower, and the infrared a little lower still. But not everything is equal. The index in the calcium K is often created by averaging over a large chunk of the line, and that has a lot of photospheric signal. If you were to do the same in the wings of the calcium 2 or in the wings of H alpha, you would see the same things.
Okay, thank you.
Any other questions? All right. Thank you so much, Garrett. All right, next up, we have Carter.
Check, check. Check, check, check. Yeah. And do I have like a, how do I advance the slide?
Or the space bar right there.
Space to advance. Okay, sweet. Fun. There's like a lot of toys up here. Okay. Fun. Okay. We good? Okay. Hello, everyone. My name is Carter Woodson. I am researching solar physics this summer with the BSA in Boulder, Colorado. My mentors this summer have been Tom Shad and Dylan Key. They are both working in Hawaii at the Daniel K. Inouye Solar Telescope, DKIST. Our project is titled Forward Modeling of Forbidden Coronal Lines and Synthetic Flares.
Yeah, there's little, see these little.
Gotcha. If I click it again, will it go ahead again? Okay. Okay. Eruptive solar flare events are the result of energy building up in the coronal magnetic field configuration and abruptly releasing as the field relaxes. Different features of the sun are observed at different wavelengths, depending on what wavelengths of light are measured. Here on the right, we see 4 SDO images of the sun, one in the visible spectrum here, the others at 304, 193, and 1600 angstroms respectively. And so the question is, what sort of signals might be observed that help us to analyze and forecast flares? And at which wavelengths of light? This is part of the motivation for modeling the sun in a simulation, as it provides a sandbox for exploring these questions. Synthesized observable quantities like photon emissions would be a consequence of the thermodynamics and atomic chemistry that we understand and inform how we observe and measure light from the solar atmosphere. This is a figure from a paper by Mark Chung and other authors that we use to guide us through the project. The paper gives a detailed description of the 3D magnetohydrodynamic simulation code used to synthesize maps of X-ray and EUV emissions here. The MPS/University of Chicago Radiative MHD code, MURAM, contains 3D cubes of values for temperature, pressure, velocity, magnetic field, etc., simulating a small volume of the sun, capturing the top 7,500 kilometers of the convection zone and 41,600 kilometers of the overlying atmosphere. Over time, the simulation shows interactions between 2 bipolar active regions and the emergence of a parasitic bipole. So Here we can see in the magnetic picture, you can see the pre-existing regions and the parasitic dipole that emerges. Along the top, figure A shows the vertical component of the magnetic field in this view, in our field of view, with periodic boundary conditions near the boundary between the convection zone and the solar atmosphere in the simulation. So this is right at the boundary between the convection zone and the solar atmosphere. The rest of the figures show the synthesized maps of distribution of X-ray and EUV light emissions at 171 and 91 angstroms. So 171 in orange and 94 in green. Figure D shows a dimming in the signal that is more apparent in 171 angstroms. So we see a dimming here in 94 that's more apparent in 171. The paper goes on to describe the relationships between the synthesized emission distributions and other macroscopic MHD structures in the simulation. Our project adds to the work done in this paper by further processing the photon emissions using the Stokes polarization parameters to get information about the polarization states of light as viewed along a particular line of sight. I'm not sure that this will play because I think it's on PDF, but we can try. Okay. The animation shows the evolution of the photon emissions distribution over time, the flare and mass ejections occurring around t equals 0. Towards the end, we see the plasma in the field relax and these defined post-flare loops near the boundary of the convection zone. So we'll see the mass ejection here. Oh, does it not play? Oh, it plays on my screen. That's not very good. Is it on PDF or something?
So if you make your arrow go that way.
You might have to do it,
Yeah,
honey.
no, you're
Yeah.
Oh, no, that's just opening this.
Okay, we'll probably have to move on. We'll probably have to move on.
It's okay. I don't think that's gonna work. That's okay. Sorry. All right, keep going.
It'll be okay. So then this screen.
Yep.
Okay. Okay. Towards the beginning of the project, I spent most of the time becoming familiar with the orientation of the 3D data cubes. Here you can see the extent of the simulation cubes in megameters from a side view perspective. These are slices along the y-axis in the XZ plane in the simulation. Each of these animations, it's important to know, and all of the ones moving forward are static in time. So single time step, no movement in time. Animations are showing several values at the same time step in the simulation, and we are looking at consecutive 2D slices of the full 3D volume. We can see similar structures for the plots of temperature and the z component of the velocity, the temperature and the z component of the velocity. We see different but also similar structures along the bottom in the z component of the magnetic field and the inclination angle of the magnetic field. So near z equals 0. The temperature and velocity go to 0 at this scale, and we can see chaotic magnetic field values where the convection zone is. This is same data, same time step, just a different view showing the temperatures and velocities in the x direction, I believe, or the z direction. So yeah, the z direction. Using the same data cubes as the previous slide. This view is picked perpendicular to the previous view and again moves through the 3D cubes, one 2D slice at a time for a fixed time in the simulation. This is the same orientation, now just showing the inclination angle and the Z component of the magnetic field. Here we see similar structures as the inclination angle measures the angle between the magnetic field and the Z axis, which is vertical here. So we see similar structures here, the white and the red. So this shows a top-down view through the photosphere. You can see the signature of the parasitic dipole as we pass through the convection zone. The scale on the temperature graph is omitted. It's an automatically adjusting scale so that we can pick out these huge variations in temperature as we pass from below to above the photosphere. And we can see a difference in the structure as we go from below the convection zone to above the overlying atmosphere. Okay. These maps of electron density were calculated using the mass density values from the simulation and help from a paper by M. Rimple, which describes their extension of the Muriam code together with the Chianti atomic database. The atomic database facilitates the incorporation of the atomic information of different ions and their emissions at different wavelengths with the MHD values. The electron density together with the Z component of the magnetic field gives us a sense of the structure of the coronal loops in the simulation. The 3D render of the magnetic field lines to the right provided by our project mentor, Dylan Key. So he's showing in 3D, I'm doing my best to show above the active regions, the coronal loops. Figure in 3D shows the topology of the field overlaid above the magnetogram map from the simulation data. We incorporate the use of the Chianti atomic database as well in our project with the help of a Python package, PyKelp, which was developed by Tom Shad, the lead mentor. The package brings together the atomic information and the MHD simulation values to calculate coronal emission line polarization. I referenced a paper authored by Shad and Dima for the project, wherein they described the use of PyKelp to synthesize polarized emission signals so that I could do the same. This is a figure from that paper showing the relationship between the upper level atomic alignments of iron-13 emissions at 10,746 angstroms. It also shows the electron density and the inclination angle of the magnetic field, the relationship between those three variables. The atomic alignment, just to give a quick explanation, is a parameter that quantifies how a particular energy level in the atom is polarized at the quantum level. The solid line here follows an inclination angle radial to the magnetic field, so radially in the Z direction. The dashed line shows a horizontal inclination angle and produces no alignments regardless of electron density. So we see the dotted horizontal line. And then that's the dashed line for horizontal. And then the dotted line shows a magnetic field inclination equal to the Van Vleck angle. So the bottom one, the dashed one. And we see negative alignments at that particular orientation. The Van Vleck angle is a critical angle where the fraction of linear polarized light is 0. Within this figure, the green line here shows these calculations at 100 levels. Basically, the figure shows the difference in using different number of energy levels for these calculations. So he's assuming a baseline of 749 energy levels, and if you use less, say 100, or even less, 27, then you'll see these differences in the values. We used 50 energy levels for our calculations using iron-13 ions. Here we see the maps for the upper level alignments, and they agree with the figure from Shad and Dima. The regions with horizontal inclination angles show no alignments regardless of their electron density, and the regions with radial magnetic field inclination and low electron density show the highest alignments. So we see here The magnetic field inclination is horizontal at 90 degrees, and we see no signal in the emission or in the alignments, which is what we saw here at the the dotted line. And here we see the temperature relationship with the photon emissions for different ions at different wavelengths. Again, we're interested in iron 13. The blue line shows, the blue line follows iron 13 for us. And we see if, and as we see, if the temperature is outside of this range, from 1 to 3.5 million Kelvin, then we see no signal, no apparent signal in the photon emissions at this wavelength. So it can be a little bit hard to see, but these plots show the maps of total emissions for each field of view, similar to the photon emission maps from Chung 2019. In this instance, we are seeing multiple steps in the simulation. This is one of the only figures that actually shows multiple time steps, with the earliest time step to the left and the latest to the right. We can see the mass ejection around between these two around here. And we can see post-flare loops after the mass ejection at the bottom towards the convection zone. So here's another figure from Chad and Dima showing the emission spectra of silicon-9 and iron-13, along with the Stokes polarization parameters Q, U, and V. The dotted vertical line around x equals 11.71. So see here as x equals 1171. This is the dashed line. I'm not doing the best job of pointing at it. The dotted vertical line acts as the line of sight for the pseudo-slit spectra shown here. The Stokes parameters are a set of values that describe the polarization states of electromagnetic radiation. The first parameter, I, is the total intensity of the emissions, and the second two parameters, Q and U, both measure the preponderance of vertical versus horizontal linear polarization at 45-degree rotations from each other. The third parameter, V, measures the preponderance of left-hand circular polarization versus right-hand circular polarization. Furthermore, Q and U can also determine, or Q and U also do determine, the direction of linear polarization related to the orientation of the magnetic field, while V grows in proportion to the total strength of the magnetic field. These plots show the 4 Stokes parameters for silicon-9 and iron-13 photon emissions for the wavelengths shown at 2 particular coordinates shown by the red circles. So below, he's showing these same parameters, but only for these single dots, single pixels, instead of the entire line of sight. We can see the effects of Doppler broadening and shift around the given wavelengths of the dependence on temperature and velocity here. Here we've shown a similar plot for a particular pixel in the simulation shown in red. So for this particular pixel, these are the 4 Stokes parameters along with the total linear polarization. Density has, to be able to see it, I had to scale it down quite a bit. And here's for a different pixel along the same horizontal line. We can see the effects of the Doppler broadening and shift as well here. So from 0, these are all shifted to the right and more broad than the previous. More spread out along the wavelength space. Okay. Here we show the complete spectra through the simulation cubes along the line of sight shown by the blue line. So here's vertical blue line and all 4 of these. We can see the relationship between Q and U, the linear polarization states, as well as the relationship between the strength of the magnetic field and Stokes V. As the magnetic field weakens, so does the signal in Stokes V. So we can see towards the bottom where the magnetic field has the strongest signal, we have the strongest Stokes V, and it tapers off as we go away from that. Here's another example of the pseudo-slit spectra, now for a horizontal plane through the simulation, as our line of sight here is indicated in blue. So now horizontal. Near x equals 80 megameters, we see a significant shift in the Stokes I signal corresponding with the flaring region we see to the right. So at around 80 corresponds with this region here in this picture. The signal in U tracks the changing orientation of the magnetic field. So we can see in U, or this one's probably the best one to see it, as it goes from black to white bands. That's the changing orientation of the magnetic field. And the signal in V strengthens as we move into the bipolar active regions. So we see a strengthening in the image in V over top both of these active regions. Okay. The figure to the left shows the emission spectrum for the first Stokes parameter along the line of sight shown below. We see significant shifting and broadening of the signal, especially as we move through the flaring region. So right here corresponds with this region right here. In order to see more closely what parts of the simulation are contributing to these signals we see in the spectrum, to the right, we see a top-down view of the plane through the simulation corresponding to the line of sight. So if you were to pick out the plane along this line of sight and rotate it so you could see it, this is what you would see. This image was taken or shown here was processed at 1,749 angstroms. Further to the right, we see shown is a plot of the total emissions integrated through the simulation cube, shown from a top-down view. So this is all of the emissions at every place. 1 minute, got you. The spatial contribution plot shown at 1,749 angstroms, if processed at a higher or lower wavelength, would show which part of the simulation in the mice are responsible for shifting and broadening that we see in the pseudospectrum. The image below was processed at a lower wavelength, and you can see what regions of the graph are responsible for the shifting to the lower wavelengths. This final slide makes the point the importance of the spatially resolved spectral polarimetry. Looking in the second row, we see that the spatial plot and spectrum for Stokes Q, the signal we see on the other side of 20 megameters, shows up on the left around this banded region. So at 20 megameters here, we can see that signal here. However, the dark band around 40 megameters is lost in the spectrum. So around 40 megameters, this dark band is lost in the integrated spectrum. Further investigation can inform as to which techniques or instrumentation may be necessary to reliably probe the solar atmosphere for these polarized signals. And lastly, I would like to take a moment to thank our mentors, Tom Shad and Dylan Key, for guiding me through the research process, and thank our program directors as well, of course. They work so hard for us to have this opportunity and are truly amazing people. Thank you. Okay.
Thank you so much, Carter. Any questions?
All right, could you go back to the MHV value slide? It's more towards the beginning.
The MHD values?
Yeah.
Yeah.
Go back further. One more. There was that one right here. Yeah. My question is, why did you just why are you not including B in your was there an image that was included?
There's an image there at B that Claire told me was not really helping my explanation, and she told me to omit it.
I see.
Because it was not really providing any information.
That was my only question.
I'm coming, Max. So, sorry. So just to clarify, in the MHD values, the animations, those are not time animations. It's
No.
going through 3D space in one given instance of time.
Yes.
Okay, just making sure.
Single instance in time.
Yeah, I have another question. Since this stepping through 3D space, my question is the way, since how are we able to see these structures? Is it through different angstroms? Or is that correct in saying that?
Yes,
Okay,
yeah,
that was
exactly.
perfect. Now I
And-
can understand now.
And so you'd have to use different slits with different properties to be able to get a wide scope of measurements.
I'm not sure if I just missed this part, but what angle are we looking at here of the sun? Is it sort of like side on?
This is
Okay.
this would be from the side on.
Thank you.
Okay, so later in your presentation, you talk about how you had broadening and shift. So in my presentation, I also I talk about broadening and Doppler shifts. So in your case here, like what does this mean for you, like for your research? Like what did you discover here?
We synthesized these emission spectrum at one particular wavelength. Oh, sorry. I should restate the question as well, huh? So we're asking about the Doppler shifting and the temperature broadening. We synthesize these photon emissions for particular wavelength, so at one wavelength. But whenever you go to observe these, they're going to interact with the temperature and the velocity. So you're not necessarily going to be able to measure that signal at that wavelength because of the Doppler shifting and the broadening. So it's important that we capture that.
Any more questions? All right, thank you so much, Carter. All right, now we've got Brooke up next. We'll get you situated up here.
Perfect. Okay. All right. My name is Brooke Cotton, and this summer my project was to improve the solar flare location data product using the X-ray sensor aboard the GOES-R satellites. I've done this with the help of my mentors, Courtney Peck and Janet McColl, and a lot of the previous work was also done by Laurel Rackmiller. Here on the slide here is a picture of our satellite. The light green-blue arrow is pointing to our X-ray sensor. This X-ray sensor is always pointing at the sun and looking for solar flares. We care about these solar flares because their X-rays can disrupt radio communications, and large solar flares can be correlated with CMEs. What forecasters really want to know about these solar flare events is if they're dangerous to Earth. To do that, they ask 3 questions. The first thing they want to know is the time that the solar flare is happening. The second thing that they're going to want is to know how big this solar flare is. And the third thing is the location. By finding the location of the solar flare in the sun, if it is a large flare and there will be a CME correlated with it, it might be Earth-directed and have more harmful space weather effects. We use our X-ray sensor instrument to detect these solar flares. Here's a solar flare on the sun. The image, you should be looking at the white flash in the center. Our detector, the little diagram, the yellow circle is the sun. The light from the sun comes into our instrument and through the aperture and is detected by these 4 quadrants. We use 4 quadrants instead of 1 because these solar flares can get large and they may saturate the detector.
It's very important to note that our instrument is not an imager. We do not get an image of the sun. Instead, we get something that looks like this. This is the information coming in to all 4 quadrants. And this can tell us, of course, when the flare starts, when it peaks, and then it decays out and ends. We can sum the information from all these quadrants into another graph that looks like this. Once again, it's a clear start, the flare peaks, and then it decays out. With that, with this information, we can determine first the time here. We have the time of the peak, the start, the end, all of that. And we also can figure out how strong this flare is. The unique part of the X-ray sensor, though, is we can also find that third part that space weather forecasters care about. And that is going to be the actual location of the solar flare. Because we have 4 quadrants, we can use some relatively simple mathematics to figure out the location. This diagram on the bottom, once again, the sun is shown in yellow. The background, which is the sun before the solar flare starts, is shown in yellow. The information comes from the sun through the aperture and is reflected onto the detector as this yellow square. That's going to be the background. Once the solar flare starts, we have more information coming in from one point on the sun. That's, I guess, the red dot on the sun, and it comes through and shows on the detector as this smaller red square. The first part in determining the location of this solar flare is to correct for the background. So we remove what the yellow square is telling us, and we're just left with the red square. This red square is going to be the location, but the actual location will be the center of the square. To find the center of the square, we look at these 4 quadrants. To find the X coordinate, we take the quadrant 1 and 2, and then difference between 3 and 4, and then that effectively finds our X value. And then for the Y value, it's the top 2 quadrants and the bottom 2, and that will give us our Y coordinate. We do have to do some corrections though. Our instrument was meticulously calibrated before launch, but after launch, there are some small, slight misalignments with the way our X and Y coordinates are. They're very small numbers, but they do exist. So we correct for these. After correcting for background, we found the X and Y coordinates for the detector. This is in a -1 to 1 coordinate system. To get this into a value on the sun, we have to do some further calculations. Let's take a look at first the X equation. Right here, we are first using our corrected for X value. Then we are multiplying by some angular offsets. This is going to be the position angle and the roll angle. These effectively line the instrument up with the sun and then the sun to Earth. So then we're seeing the flare as the Earth would see it. This whole thing in parentheses is still not in units that we want, so we multiply by this f of x, or field of view parameter. This field of view parameter depends upon the location from the detector to the aperture, and also the size of the aperture. This is the same for the y equation and the field of view y. I stated that these 4 parameters that I've highlighted now can change. The field of view changes because, of course, those distances and the sizes may change very slightly after launch. The focus of my project is to find the best set of these 4 parameters to find the most accurate locations we can. We do have a rough idea of what these values might be, but not exactly. So to figure out the best set, we'll just be guessing. Here is a picture of this flare we were looking at. The actual location is indicated by the red diamond here. Let's just guess, take a stab at what these 4 parameters might be. We've guessed for the X and Y offsets, as well as the field of view X and Y, and we've gotten a location 300 arc seconds away from the true location. I think we can do better. So we guess again. We've guessed with different parameters, gotten a new location, but we are still quite a bit off of the true location. Let's guess maybe 10 more times. All these guesses are showing up on our sun, and we can compare them to the true location in red. To me, it looks like this one here that I've highlighted in blue is the closest. So for this flare, this would be the 4 parameters that would best suit it. 50 arc seconds is not really ideal. So we would like to calculate, to estimate and guess more and more times. Yes, so to do this, we enlist the help of a computer. What I've described to you is a Monte Carlo method, so that's guessing many, many times. In this graph here, each of the black dots represents a guess of what our y offset parameter will be. In the x-axis is the actual value of the y offset, and then in the y-axis here is the error in location. We want the smallest error, which means our calculated flare and the true locations are closest together. And this is marked by the red dot here. Let's actually zoom into this graph because it looks like the red dot is slightly less than 0. It is. Here is a zoomed in version. If the offsets if we did not need to correct for the offsets, this would be 0. It clearly is not. So there is some fluctuation of what's happening on our instrument. I do have to clarify here, our goal is not to define a set of parameters for each flare. Our goal is actually to have one singular set of parameters that works on all the flares that we do in our instruments. This summer, I've been calculating one set of parameters for both the GOES 16 instrument and the GOES 17 satellite. These are different satellites, so they will have different parameters. Going forward, how did we do this? We did this back in 2020, actually, and we used a larger set of flares to find the best set of these parameters. In this kind of busy plot here, it's using the same diamond circle as we used before. The diamond is the true location, and then the circle is our location. They're connected by a thin line, if you can see it. It's also maybe useful to note that there are many different classifications of flares. The M and X class, the blue and red, are larger flares, and we can have more accurate locations with these. But for the C class flares, there might be some outliers. We went back to recalculate these parameters in 2022. We've had over 2,000 more flares since then. This is the flare set that we were working with to do recalculations. And it's not ideal for maybe one apparent reason. Some of these flares are off the sun, and these are circles off the sun. So our detector was telling us at that time, whoa, we found a flare, the location is not on the sun, and that's clearly not right. We do not want to use these flares to calculate the parameters because they might bias these tiny, tiny numbers. Let's take a little look at what's actually happening. What was our instrument seeing during these times? First, though, let's take a step back and look at what a typical flare looks like on the sun. On the plot on the left, this is the information coming into our instrument. For a typical flare, we have a defined start and then peak. The important thing being in this plot is the orange dots here. The orange dots represent the background. If you think back to that image of the sun coming into the detector, that background is going to be the yellow square. So we have a good background. The background is low relative to the peak. And that's a fantastic flare to calculate a location on. In the case of these flares that are off the sun, there were 2 flares happening at one time. The first flare in this set is a perfect one to calculate the location. The background orange dots here are relatively low to the peak. You can see the first peaks in the red circle, but then while the first flare is decaying, a second one starts. And because this first flare is decaying and the second one has started, we have an unstable background to use for this location. We heavily rely on the stable backgrounds to calculate the location of flares, and we decided we want to exclude these flares with unstable backgrounds. They might bias our free parameters. We did some filtering to fix up this flare set we were using. We first removed the second of 2 flare systems, and then we also decided to only use flares after 2019. This was because the roll angle was tracked. We had an idea of what the roll angle was, but now we're recording it, so we have even better locations. We also will only be using large M or X class flares. This goes back to the background. For this good flare here, the background, the orange dots, are relatively low compared to the peak. This might be maybe I guess for our purposes, we'll say it's an M class flare. But for one of these smaller flares on the end, the background is low, and then the peaks are smaller. And that would be a small C or B class flare. Because the background is lower, we don't have this accurate of locations. So we decided to just use these larger flares. Here's a reminder of what our flare set looked before filtering out these flares. We had some flares that were off the charts, and we can expect after filtering, it'll look a lot more clean. And it does. A lot of those things off the disk have disappeared. Specifically, this one in the red circle that we looked at was a double flare system, and we removed it because we took out all the flares with unstable backgrounds. We have a wonderful new flare set here, so it was time to recalculate these parameters. We recalculated the parameters for the X and Y offsets, and then the X and Y field of view. After finding these new parameters, we've improved the location accuracy in the flare set with a 40% improvement in intense flares, which is fantastic. You may notice, though, that the results for the B class and C class flares for both GOES 16 and 17, there's not much improvement there. This goes back all the way back to the background thing again. For these small flares, we don't really have as much data to work with, so it may be harder to get a location, even without correcting for these offsets. But our MNX class large flares have improved a lot. Our results showed that the error is less than 30 arc seconds in all of these numbers. For scale, I'm bringing back our sun plot here. This little red line or red dot represents 30 arc seconds. And right next to the sun, it looks like a really, really tiny number. So we have improved these by a lot, and we have good predictions as to these locations after updating the parameters. In the future, we will use this method to recalibrate the parameters for GOES 16 and 17 as needed, as well as use this method to calibrate locations on GOES 18, which launched in March, and then GOES 19, which will be launched in the next few years. We also want to find a method to locate solar flares when the background is poor. For an example, this would go back to this double flare system. We want to determine how we actually correct for this unstable background. The last thing we wish to do is add a data quality flag to indicate the confidence in our location. For example, a B or C class flare, we might be less confident in the location because they're smaller. This would also be, once we correct for this poor background, we would say, hey, forecasters, we found a location, but we're not so confident it's correct. In summary, I've talked about how we calculate locations of solar flares using our quadrant photodiode detector. We also realized that we have to correct for these offsets. We did this using a Monte Carlo routine, and we used a big set of flares to calculate these parameters. We've improved the locations of large flares by 40%, which is fantastic. And this method will be used as needed to calibrate parameters on all the GOES-R instruments. Congratulations, folks. You made it to the end of Wednesday presentations. Yes. I'd be happy to take any questions now.
Thank you so much, Brooke. I see Max's hand up first. So I'm gonna go over here. I might not have been looking anywhere else. I just want to say that was a very interesting presentation, Brooke. I wanted to know a little bit more about the Monte Carlo method of guessing. So if you go back to it,
yeah,
I was really interested in how the model, I guess, or the guesses are weighted. And
I'm clicking, but it's not doing the thing. Oh, you're kidding. Okay.
tell me when to stop.
Wait, no, you passed it. We want this one. Yes.
Oh, I wanted to see the distribution.
Yes.
Yeah.
Yes. Yes. Thank you so much.
Yeah, because I wanted to, I guess, know how the method is weighted because it looks like a
Yeah.
very even distribution of guesses. So I was curious how that worked.
Yeah. I am not actually showing you the full picture here. So we're not just optimizing one parameter at a time. We optimize all four. So we randomize all four, and then for each guess, you can imagine maybe the Y offset, the guess was good and accurate. The X offset was good and accurate, but the field of view parameters are way, way far off. That would, leave something right here. And it's just because we use all four parameters at the same time. Does that answer your question?
Yeah,
a little
helps me
bit.
understand what's going on here. So
Okay.
Thanks a lot.
All right, more questions. Bryce is on my way. So.
This might be a question for you and your mentor. So you said that it's really nice to be off by you're off by a few arc seconds, right? That's really good. But what about flares that are on the side of the sun and you're off by 5 or 10 arc seconds and it's off the sun still? Because that might show us, that might be that's a really good, it's not that far off. but
Like
it's still-
in this,
Yeah,
in
like,
this
yeah,
type
exactly,
of situation? Yeah. Could you repeat your question again? I'm
So
sorry.
my question is, how are you going to account for being off by 5 or 10 arc seconds, but that 5 or 10 arc seconds are not on the sun? For flares that are on the side of the sun, like on the limb of the sun. That's my question.
I don't think I can answer that entirely. Our method kind of assumes the sun is flat in this way. At least that's what these plots show. So if something's on the side of the sun, we don't really care as much about it because as viewed from Earth, if it's on the side of the sun, it's less likely there will be a CME. I will look into that though. That's a very interesting question.
Okay, thank you.
Right.
Hi, and congratulations for all of your presentations being done for today. My question was over here at the same plot. So I was wondering, after you did the filtering of this method, you still have some points on the outside. What might those be?
Okay, we're gonna go. Let's compare these two, right? So this was before we did our filtering and after, and there still are some really funky ones. I cannot tell you exactly what's happening in all of these, but I can notice here that most of the ones that are off the sun are actually green, which means they're C-class flares. And in the end, we will not be using them for our calculation. I That's all I can say now.
I think Gabby was next.
So you were talking about your background. So is your background, maybe I missed it, but is it coming from like the rest of the sun? Is that your background or is it like instrumental? And how do you know that, like on that flare where you showed that there was a like a double flare, how do you know that is another flare and not just more noise?
Yeah. Oh, this might be good. Okay. Okay. So the background that we use is actually oh, I went too far. 8 minutes before the flare starts. So that background is affected when there's a double flare because 8 minutes before the second flare started, the first flare was already happening. So it's at 8 minutes there. We can tell visually that these are double flares. I wasn't completely truthful. This flare here is actually a double flare. Oh, wait, no, I have a wonderful picture here. The sun, if it's still moving for you guys here, you can see this is the flare I'm plotting here, and that's this large peak. But there's actually a second flare happening over here. If you wait for it to flash, that's a very small flare. And that's going to be where this first peak is. Being it was so small, it didn't really affect our measurements, but that's kind of how it works. Yeah.
So when you said that you remove the double flare, are you removing just the second flare or are you removing the whole double flare together?
We are just removing the second flare.
Okay.
Yeah.
So I would like, I'm curious to know more about what is so special about the 4 quadrants in the detector. And I know you touched on the single, why the single window is not good.
Yeah.
What about, making 8, like a pie with 8 slices in it, or like something like why is 4 so special?
That's a good question. We actually have 4 of these quadrant photodiodes. So I guess in total, there's 4 of these quadrants. The first one measures like when there's no activity on the sun, just a stable background. But when you get more X-rays, it switches to the second one. We found that system works well. I don't know why we can't add another one. That would be interesting. I'd like to see it. But that's probably a Courtney question.
All right, thank you. Any more questions?
You alluded that you want to use these double flares. Do you have ideas of how you're gonna? It's kind of a hard question because this is your future work. I'm asking like,
yeah,
what ideas do you have for that?
Yeah. So the goal is we don't want to use these double flare systems to calculate these free parameters. We're not very confident in the locations, but we do want to fix this problem that's happening. We're thinking of maybe doing some modeling. When the first flare is happening, we could model the curve, like what's it going to look like after the decay, and then from there we can find the background.
Right.
But I'd be interested if you have any ideas.
Okay. Thank you. Great presentation.
Thank you.
All right, any more questions? Thank you so much, Brooke, one more time.
Thank you.
Yeah, so great job, everybody. We finished Wednesday presentations. Cheer a little bit. That would have been awkward for me if no one said woo, but thanks, Willow.
All right. Yeah. Should we disconnect from the live stream and then do a little bit of a debrief? So if you are on the live stream right now, we will see you tomorrow at 9:45 for the next session of REU talks. There will be 10 more talks tomorrow. So join us tomorrow at 9:45, and then on Friday for the poster session, which is in person only. So thank you so much for joining us today. All right, folks in the room, stay around. We're gonna debrief after they can't hear us anymore.
Yeah, I hid the meeting controls.
Killing it.